Greetings everyone. It's 3 p.m. But let's wait for a couple of minutes so that the people can join the session. Hi everyone. So basically, let's wait for 1 more minute, and after that we can start the session. If you feel you have any question, you can unmute and ask in the beginning. If you have any doubt, wait a second. So I am assuming that we are having no doubts. So let us start this session, uh, session 2. Uh, this course is basically being taught by the Professor Sanjeev Sambadan from IIC Bangalore, and we have two instructors for this course who are doing this live session, weekly live sessions. Uh, and today, as usual, has been reshared last. Okay, Neeraj, you can check it on this course website, which is the Semiconductor Device and Circuits. There they have shared one link where there is a spreadsheet, and you can check both the TA's YouTube links and the course folders where we have shared our PPTs as well. You can check it on the portal. Okay, fine. So I think you are not being that interactive. The audience is quite mute. So let me start with this question, which is about the wave functions. Which is about the wave functions. So I want anyone among you to answer this question. Let it be wrong. You just need to provide some answer to this question with a little bit of logic. You can either type in chat box or you can unmute yourself as well. I have no problem with that as well.
It should be normalizable so it doesn't blow up.
Okay. Which option are you going to select among these four options?
C.
Okay. Basically, this wave function, this has some information. I would say all the information about the particle that we are going to study. So this wave function, if it has to be realizable, it has to be normalizable, which means that this particle has to exist in the space. So this wave function, if we select this option, we have to go with the C, as the Neeraj told correctly, that this wave function must exist somewhere in the space in order to be normalizable. Now, what about this second question? As we have seen for this psi, we have seen that it must satisfy certain properties, and to satisfy those properties, here we have given four wave functions, where uh, among these four we have one which is not valid, which does not satisfy the properties of the wave function. So can you comment on the graphs, which one?
Is it the last option because it is not continuous?
Yes, absolutely.
The last
Going
response.
nice. Can anyone else also comment on these other wave functions which are present in this? Like we have this Sheikh Shah, Tejaswini, or Mr. Shirihari, or Mr. Ashaji. Can anyone among you also comment?
Other wave functions are found to be continuous
Okay,
other than the last option. So the primary condition for the wave function is it should be continuous and also its derivative must be continuous.
absolutely. That's what I wanted. The derivative as well. So as Mr. Shirihari also told, that its derivative must also be continuous. So we have, whenever we look for the wave functions, not only it should be continuous, its derivative should also be the continuous. So if we see, as told by the Neeraj, that this option D, this should be invalid wave function. So we will select this. Wait a second. Okay, Neeraj. Yes, yes. You can ask. You have raised your hand.
Wanted to ask,
Okay. Did it happen by mistake?
hello.
Hello. Ha ha ha. Hello.
I'll type. I'll type. I'm traveling on bike. Sorry.
Okay, okay, okay. No problem. No problem. Okay. So Neeraj will type. Till then, this option D seems to be the correct one to go with. Now, as we have been. Wait a second. There is some message. Okay, it's fine.
Sir,
Yes.
how to find the function is normalizable, like just seeing the diagram?
Okay, you can see one thing over here. For example, if I draw any wave function over here, you can see within the limits. Let's take this function for example. You can see within the limits of minus infinity to plus infinity, it is existing. It is not exploding. By exploding, I can say, like, if I have some wave function like this, which goes on increasing, like exponential function, which goes on increasing continuously within the limits, and it explodes at x to the power of infinity. So if this is x and this is some function, any function, and you are not able to contain it, you are not able to hold it, so this means that this wave function has exploded, and as a result of which its presence cannot be confined to the limits of range minus infinity to infinity. And for that, you can say that whenever you are normalizing any quantity between the limits minus infinity to infinity, you are having some normalization constant in order to have the probability confined to a value of 1. And this small trick helps us to check the whether these wave functions are normalizable within the limits of minus infinity to plus infinity, within the limits of. Okay.
And sir, for derivatives with, I mean, for graphs with sharp edges, why do the derivatives are not continuous?
What?
When we, let's say, the graph is an inverted triangle,
Mm-hmm.
so for such graphs, we say the derivative is not continuous, right?
Yes.
Why do we say that?
Basically, you can go into the mathematical course for this. It's just when you tend to approach a function from minus infinity. Let's say we have to check a function at 0. We have to approach it from 0 minus, and we have to approach it from 0 plus. We have basically two limits to approach it. And when we approach it from one say 0 minus, and when we approach it from 0 plus, let's say, or a minus and a plus value, you will obtain two different values. So you have to do a bit of mathematics for this. Okay. Yeah, it's just mathematical problem, nothing more like anything. There is nothing physical about that thing. You just have to check the limits of approaching from the minus L and plus R. So that's basically only thing that you need to check while checking the derivatives. Now there is one problem where it has been told these problems. I guess you might have solved these problems uh, in the course itself, which professor taught. He might have told you about this amplitudes, the interferences, how these intensities are related to the amplitudes, and how we can have these constructive interferences and the destructive interferences. And now over here, this is a mathematical problem. So this is simply some mathematical problem we are going to solve. And it says that that if we have this ratios of the intensities in this some interference pattern, which is given by the ratios of 25:1, which means that the maximum value will be 25 times the minimum intensity. So from these two ratios, we are required to find the ratio of the amplitudes of two interfering waves. What would be the amplitudes of the two interfering waves? Now this net, or what we can say, this net intensity is defined by the I1, where I1 is intensity and I2 is also the intensity, and these two intensities are interfering with each other with some value, with some angle. We can say this interference, this in one second. Okay, Anardam has joined. Okay, fine. So this phi will denote, this cos of phi will tell us about whether we are doing it constructively or whether we are doing it destructively. So in here we also know that this intensity has some proportionality to this amplitude, which is directly proportional to the amplitude square. So if we try to write this net thing, this net intensity thing in terms of the amplitudes only, we would simply write this a I1 to be proportional to the A1 squared, this A2 squared plus 2 times A1 A2 cos of phi. Now we have two cases. One is for the maximum intensity. For the maximum intensity, we say that this, let us take one value for phi, which is 0. For this will be constructive interference cases. For the multiples of n and 2 pi, we can say that this value is having maximum value, this intensity is having maximum value for theta equal to, or phi equal to 0, and it will be having minimum intensity when phi is equal to 180 degree. Okay, so we can now put these values for this phi and obtain the values of this maximum and the minimum amplitude by taking the maximum intensity value, which will be A1 squared plus A2 squared plus 2 times A1 A2 cos of 0, which is 1. Let me write it down like this: cos of 0, it will be simply equal to A1 square plus A2 square plus 2 times A1 A2, fine, 2 times A1 A2, and this simply is equal to A1 plus A2 whole square. So this is for the maximum case. Wait a second. So this is for the maximum case. Now for the minimum case, okay, for the minimum case, we are having the value to be equal to A1 square plus A2 square minus 2 times A1 A2, because cos of 180 degrees is minus 1. So this is simply equal to A1 minus A2 whole square. This is the I min. Now I max we got to be equal to A1 plus A2 whole square, and I min to be equal to A1 minus A2 whole square. Now this value has to be equal to 25:1. Simply this is equal to 25:1. A1 plus A2 whole squared, A1 minus A2 whole square. So if I take the square root, it will simply be 5 times A1 minus 5 times A2 equal to A1 plus A2, or simply it would be 4 times A1 equal to 6 times A2, or A1 by A2 is equal to 4 by 6, which is sorry, A1 by A2 is equal to 3 by 2, which is 1.5. Yes, it is 1.5. So let's check if any option matches. Yes, option B is matching with our option this answer, and so this option B seems to be the correct one. Now uh, uh, let us move to this another problem, where we have been told to calculate the width of a well. uh, have have you solved the problems related to this infinite potential wells? I guess yes, you have solved it in the lecture as well, and in the previous what we can say, in the previous live session, we also solved the problems related to this infinite potential well. And you must have gone through this uh, in previously, that whenever we are solving for the energy for this infinite potential well, it comes out to be equal to h bar square k square by 2m. This was the energy that we had obtained for this case, and we had obtained some condition on the values of k when we were dealing with this infinite potential well. This is the general thing, and we had obtained for any n, this energy value will simply be n square pi square h bar square by 2m L square. Now this electron in this is in only in 1D, so this is 1D problem. So this has been thought to be present in the fourth energy level. As you know, this discretization of energy, what you must have seen in back in class 12th, 11th class standards, and you know that how these uh, electrons jump from high energy to low energy, dissipating some photonic energy, heat energy. So in here we have been told that this emits some light when this transition occurs from this state or energy level, which is fourth energy level, to the ground state energy level. In the case of an infinite potential well, we will be having this release of energy, and this release of energy in here is given by this photonic or light emission, where this wavelength, since we know this wavelength has its association with the energy with some formula that we all know, and this association is basically the release of energy that is happening when we are transitioning from a higher energy state to a lower energy state. So simply over here, if we can say that this n is equal to 4, and for the ground state n is equal to 1 for our ground state. Now if uh, let me uh, let me ask you, what would be your approach to this problem if I have two energies? For example, I am transitioning from a higher energy to a lower energy, and this how would you approach this problem? Can anyone ask? I would say, can anyone tell? Sorry. Be
When
it
an
wrong.
electron jumps from higher energy level to lower energy level, it emits the energy. So we can calculate the energy difference from E4 to E1.
Absolutely, absolutely. You are going amazingly well. Yes. So this is just basically the energy conservation that we are going to do. Nothing else. So we would say that, since, as Mr. Shri Hari told, that we will be transitioning from this higher energy to a lower energy, and that difference we will be equating it to this wavelength, the energy that's associated with this wavelength, and we should get some relation. So let's check this, whether we are right in saying so or not. So if this E4 is this fourth energy level energy, so this will be simply equal to 4 squared pi square h bar square by 2m l square. And for E1, we will be simply having 1 square pi square h bar square by 2m l square. Now this sorry, yes, this now we have to do this energy conservation, and this we can say this delta E, some delta E, which is this E4 minus E1, is simply the difference between these two energies, which is 16 minus 1 pi square h bar square by 2m l square, which is simply equal to the value of 15 pi squared h bar square by 2m l square. Now what we are required to do is, we are required to find the this energy associated with this photonic transition that is happening in the form of light. So this basically these things also require the momentum conservation extra, but let's consider that we are just transitioning at some value which is a fixed value. Let's say we are transitioning in a band structure. For example, if I have some material which is a direct band gap material, and I am transitioning at some point which is associated with k equal to 0. So let us say that we are neglecting this currently this momentum, what we can say a momentum conservation. And we are only interested in this energy conservation, although this energy and momentum they are related. So this this energy value what we have obtained over here would be simply equal to this photonic energy that is being emitted. We know this energy is simply given by E equal to h nu, where this nu is the frequency. However, this we have been given to the value to be equal to h lambda c bar by lambda. Since we have been given this wavelength value, we know this nu can be represented by this c by lambda, and we just have to equate this delta E with this E to obtain our value. So it will simply be equal to hc by lambda, and this will be simply equal to h. Let me write it down like this. This is equation 1, this is equation 2, equating equation 1 and 2. So simply this is, since this is h bar square, this is h bar square pi square by 2ml square, which is multiplied by 15. So this h bar square is simply h by 2 pi. So we can write it to be equal to h square by 4 pi square, so that this pi square and this pi square gets cancelled, and this one of the h also get cancelled, hc by lambda. So let's cancel these values, this h square, this pi square, and sorry, this is having something in the denominator as well. This is 2ml square. So this will give us the value of L to be equal to, simply equal to, L is equal to 15 times lambda times h divided by 8 m c under root. Yes, this is the value of L. Yes, so this is the value of L. Let's put the values for these constants. This h c, the mass, I think it must be given. Yes, it is given. It's 9.11 into 10 to the power minus 31 mass of the electron, and this h is given to be equal to 6.26. This is the Planck's constant into 10 to the power minus 34 joule second, and the velocity of light is given to be equal to 3 into 10 to the power of 8. So let's put these values. So this is equal to, sorry, this is equal to, L is equal to 15 times this wavelength, 20.9 nanometer, which is 20.9 into 10 to the power of minus 9 meter, times this h, wait a second, let's start this, times h, which is 6.626 into 10 to the power minus 34, 6.626 into 10 to the power minus 34, into 10 to the power of minus 34, divided by 2 into m is 9.11 into 10 to the power of minus 31, into this value, which is c, 3 into 10 to the power of 8, sorry, 2 into 4 it should be, so it should be 8 into 3 into 10 to the power of, so Let me solve this. It will simply be 15 into 20.9, 6.26, this is coming out to be equal to 9.5007 into 10 to the power of minus 40 will go above, and it will be minus 40, and it will be minus 42, it will be minus 2, and it will be 10 to the power of minus 20. Yes, 31, and it will be it should be minus, yes, it is this under root. So it would come out to be equal to simply root of 9.50, root of 9.5007. It would come down to 3.082 into 10 to the power of minus 10 meter. So this is the value of this L. This is the width of this valve. So okay, it's a nanometer. The answer is a nanometer. So it would simply be equal to 0.3082 nanometer. Let us check. Yes, option B is closest to our value. Our value is 0.3082, which is the 0.3082. Yes, it is the closest value to this thing. So it will be option B that we will be selecting. Now this is another problem related to this normalization, where you can see this clearly shows one thing, which is uh, uh, whenever we are having this wave function, we are normalizing it with some constant value in order to have this probability defined between the limits of minus infinity to infinity. So this wave function over here, it says that this wave function is simply this psi of x is equal to 0 if x is less than 0, and it is equal to some function a root 30 times x L minus x if this lies between 0 to L. Okay, and also it is 0 if x is greater than L. So now we will do this same old trick. We will say this, we will integrate it between the limits of this minus infinity to infinity. Since this is a real function, it would simply be psi of x whole square minus infinity to infinity dx equal to 1, and from this we can find out the limits from this function. Its limits are between 0 to L. So these are the limits for this function, which is given by a square. Let's do it separately first so that we don't get confused. Okay, it will be a root 30 x L minus x whole square dx equal to 1. So let's take this constant outside. A square 30 0 to L x square L minus x whole square dx equal to 1. So let us do this integration. So we can either multiply the two functions, or we can do the integration by parts. I think let's solve it by integration by parts. So it would simply be a square 30. This is 30 a square. This is 30 a square. And since this is x square L square minus dx, it will simply be, if I integrate this function, it would simply be between the limits minus x square L minus x cubed by 3, 0 to L, 0 to L, and this will be simply plus derivative of this x is 2 times x, 0 to L, 2x, L minus x whole cube dx equal to 1. Yes, this is what we get. From this, you can clearly see, if we put this equal to L, x equal to L, this thing will be 0, and if we put this thing to be equal to x equal to 0, this thing will be 0. So between the limits of this 0 to L, this is this function which is on the left hand side of the equation, this is equal to, simply equal to 0. Now let's concentrate on this thing only, this thing only. It would simply be equal to, if I solve it, it would be 30 a square in multiplication, and this will be 2 by 3, 2 by 3 will be there only, and it will be minus 1 L minus x to the power of 4 divided by 4 times x with limits between 0 to L. This will again be plus, and this plus will make it uh, plus L minus x to the power of 4 by 4. X has been derivated, 0 to L dx equal to 1. Okay, so this is in whole multiplication with this thing. Okay, it's fine. So if I put the values over here, again this thing at L equal to x equal to L, this will be 0, and at x equal to 0, this thing will be 0, making this whole expression to be equal to 0 again. Now we are left with this thing which is 30 a square divided by, have we skipped something? Have we skipped something? Yes, this 2 by 3 is missing, I guess. This 2 by 3, this 2, since we solved this thing over here, this 2 by 3 should have been over this place as well. So this 2 by 3 is missing, into 2 by 3. Okay, yes, minus 1 times L minus x to the power of 5 divided by 4 into 5 with limits between 0 to L is equal to 1. So I guess now it is correct. L
Sir,
minus x.
second line,
Okay, where? Yes, yes,
the
yes, you can
second
speak.
line, is it okay that we have integration by part second expression 2 by 3, 0 to L, L minus x by whole power, is it 4 only, sir, or 3?
It should be 4. I have integrated this thing. L minus x by raised power 4 by 4, and derivated this thing.
Yes, yes. Okay, okay. First expression we have derivated.
Hmm.
Uh,
Hmm. First,
okay.
I
Second,
took this
second
as,
one.
speak, speak.
in second line, first expression,
Mm-hmm.
minus 1, you have already derivated the x right there, right, sir?
No, no, no. This is this L minus x cube. This thing.
Oh, okay, okay, okay.
This is this L minus x cube thing. So that's why it's coming out to be minus. Otherwise, it would have come out to be equal to plus x plus 1. And it would have just expanded our process. So,
Yes, thank you, sir.
so I guess this is the correct thing we have done. And for x equal to L, this will be 0, and x equal to 0, this will be plus. So this would, it would simply be equal to, let us solve this first. It will be 10, and it will be 20 then. This, if I cancel this, it will be 2, and it would simply be equal to this 2, and this 2 will go, and I will be left with a square times L to the power of 5 is equal to 1. Yes, this is what you should get. Wait a second. Please turn off your videos. So this is the value. Sorry, but we have okay. We have to get it in this form. So this value has to be for the or a has to be equal to 1 by L to the power of 5, or 5 by 2, or a has to be equal to L to the power of minus 5 by 2. So option A seems to be the correct option for this, and we can select this option. Now this is another problem related to this electron in 1D potential well, where this electron, uh, this time we have been given the width of this well along this x direction. This is equal to 7.3 nanometers, and the system is at state n equal to 3. So we have been told to find the this probability for this electron per nanometer length at a particular value. Since this wave is having this probabilistic nature, we cannot say that this wave is present at a particular position. So there is has to be some probability associated with the wave for being present at a particular position. So this probability governs the amount of presence of this wave at a particular x coordinate. So if we can see this solution as we have seen previously for this one-dimensional quantum well problem, we have seen this potential well problem. We have seen this psi of n is simply given by root of 2 by L sine of n phi by L of x. This is the solution for this quantum well problem, and this probability is simply this psi s psi into psi conjugate into psi, and for this case over here we are simply having this to be equal to uh, this is the real function itself. So this will simply be equal to this. Let me write down it explicitly. This probability of finding an electron uh, at some x is given by simply this probability is simply equal to psi n of x square. this psi conjugate into psi, and this would simply be equal to root 2 by L sine of n pi by L x whole square. Okay, so it would simply be equal to 2 by L sine square n pi by L x. Now this value of this value, uh, this is having the value of n is having the value of 3, and x is having the value of 0.3 nanometer. So this is just the matter of putting the values. L is equal to this potential width is equal to 7.3 nanometer, 7.3 into 10 raised to power minus 9, sine squared n is equal to 3 n pi, and this x is equal to 0.3 into 10 to the power of minus 9 divided by L. L is 7.3 into 10 to the power of minus 9. So this would simply go, and let's calculate the value for this thing. Sine square this thing, let's calculate it for this thing. It would simply be equal to square sine of 3 pi into 0.3 pi 7.3. Okay, it would simply be equal to, okay, it comes out to be in the radians, so it comes out to be equal to mm, so it comes out to be equal to 2 into this value 0.142, this value divided by 7.3, 7.3 into 10 to the power of minus 9. So if I divide this, it would simply be 2 into 0.142 divided by 7.3. Okay, comes out to be equal to, wait a second, sine of 0.123 pi, point 2, okay, comes out to be equal to 0.0389 uh, divided by 10 to the power minus 9, since it had to be in per meter. So this is the value. This is actually the value is for this probability. This has to be 10 to the power of minus 9, since this was in per nanometer length at x equal to this thing. So this probability per length nanometer is 0.0389. So option A seems to be the correct option to go with. So we have selected this option A. Now again, this So this this is another interesting problem where we have been told that these electrons are accelerated by using some external potential which is given by the V units. So it's not in electron volts, it's in volts, and this uh, then falls on a pair of slits as we have seen previously this slit experiment, and this results in some interference pattern, and these interference patterns they have that they show that these electrons have a wavelength of 1 nanometer, and we have been told to find this potential value, what external potential that we need to give to these what we can say to these uh, electrons in order to have uh, such such wavelength. Can any one of you what I can say unmute and tell me how I should approach this problem? How do you think I should approach this problem? Anyone? Tanish?
Is it going to be like Planck constant divided by root 2 ml?
Uh, that is where I just want some what we can say a brief logic behind the solution of this problem. How I should select or how I should.
We have to equate the kinetic energy of the electrons with the electric energy.
Oh, nice. So this is what we should do. We should go for the energy balance. Nice, Tanish. You also said it correctly. Uh, but as this Mr. Shrihari told, that we have to go through the energy balance. We have to. Uh, Please don't leave this session. I am just asking so that that's why in the previous session I don't ask anything. I didn't want to ask anything so that people don't leave, and I just solved the problems. If I ask you some question and you leave, it is just you are just telling me that I shouldn't ask you anything, and I just solved over here, which is also fine. I have no problem with that as well. I will just write some solution over here, and you will try to understand. I have no problem with that as well. But I want you to interact with me so that I feel that I am talking to someone who is willing to respond. By just leaving the meeting, it just means that I am bound not, I am bound by you people not to ask you, which is not a good thing for me or not you as well, because I feel that if you ask me some questions and if I try to answer those, I might be wrong many times, but I will be learning with you, and you will also be learning, because by mistakes we learn, and by mistakes only we learn. That's the only thing that help us to learn during the phase of these studies. So if I ask you something, you just do not leave. I myself might be wrong in saying some things. So after the lecture, or after the what we can say, this is not a lecture, after this discussion session, you can say that, sir, I think you were wrong in saying this. Not sir, by name, you can call me by name. Atif, you were wrong in saying this. I might be wrong. I am saying that I might be wrong because I'm not completely knowing everything in the field. I Even Tanish, he might be knowing some concepts which might help me to understand some things which are related to my field, the current field, because these basic things that that enlighten some other persons. Sometimes you say, for example, I say that this A plus B is equal to some number. And sometimes you say this, if you are saying some sort of a problem statement to a person like me, you are saying that this A plus B is a some number, and I am kind of a stuck in similar kind of a situation where this method holds, where I had to do this A plus B equal to some number, but somehow I skipped this idea. But due to your presence of mind, due to your sharpness, you enlightened me and told me, sir, you can do it like this. And this will not only help me while teaching this thing, it will help me in the future things also that I am going to do or you are going to do. Because if one person here asks one question, not he himself learns, not only I learn, the rest of the people who are present in this meeting, they also learn the same things. They, if they feel that, if they feel that he is saying something wrong, I guess he is saying something wrong, they go uh, to their places, they bring out their laptops or their notebooks, they google it, they search it, they try to find it in books. I think this person was saying wrong, so I must tell him that he is wrong in this thing, and he will correct me. By leaving this session, just it means that you are not allowing me to learn, or and also you are not allowing yourself to learn as well. This doesn't seem to be fair with these kind of sessions which NPTEL team is organizing. They just want the people participation, no matter what they ask. Even if some person might feel that this is a rubbish question or I am answering some rubbish thing, but in reality nothing is rubbish. In every what we can see word that you are speaking, there is some background, there is some concept related to it. So if you answer any question whether it is wrong, I won't judge anyone, because mostly I don't know any one of you, mostly not, I would say, rather I would say I don't know any one of you, you also don't know me. So if you say anything wrong, I will forget in 2 or 3 days, but the results of that thing would be much vast, because I would feel that, yeah, I told something wrong, or this person told me something wrong. I should go and search this thing. When I would be searching this thing, I would search 10 more things related to this particular topic, and I would get more insights into this topic. So by, if I am trying to ask you how we should approach, please do not leave the meeting. Just stay in the meeting. If you do not want to answer, please do not answer, but stay in the meeting. Do not leave the meeting, because this is being organized by huge efforts by the NPTEL team, so that we all can learn. The main motive is that we all can learn. So let's, as Tanish and Srihari, they both told that we should solve it by using some approaches. Like we should try to see that we try to see the energy balance thing, because this energy balance thing, when we will move to the energy band diagrams as well, we will see everything is energy balance. Whenever we try to balance these energies, we are able to make the band diagrams. We are able to do the physics just by doing this energy balance thing. In here it is some other thing which is energy balance. We are just equating some potential energies and the kinetic energies over here, but this also has some deep understanding which is related to your future work, where we will be solving, like for example, simple p-n junction problem, how these bands bend, how this energy balance equations or help us to understand this transfer of these energies at the interfaces. Like those things, those minute things, they just come from these concepts which you are telling me. They are just the building blocks of these things. So it is better if we stay in this session till the end, and we all try to learn together. That's it. So as both of the gentlemen said, that we need to try to use this Heisenberg's uncertainty principle as well for the second part, and we should use this energy balance as well. We should try to use the energy balance. Now uh, we know this, since this energy, this potential energy, it is given by this V, this by energy balance, we can simply say this QV is simply equal to this h bar k square by 2m, or p square by 2m, which is this energy balance simply. So let us check the values we have been given. We have been given this lambda value, I guess. Yes, it is going to be equal to 100 nanometer. We have been given the mass value, which is equal to this 9.1, and we have been given the value of this Planck's constant as well. So we have been told one more thing, to ignore these relativistic effects, so that we do not confuse ourselves with the other things, and we take the rest effective mass of the electron. That's the main motivation behind this. So this V can simply be given by mm, h square by 2m lambda square, where this has to be divided by qv. This is h square. Let us put the values for these things. This would be simply 6.626 into 10 to the power of minus 34 whole squared, and this will be simply 2 into mass is 9.11 into 10 to the power of minus 31, and this is equal to lambda square. This is 100 nanometers. This is 10 to the power of 4, 10 to the power of 4 into 10 to the power of minus 9 square minus 18, and this is equal to 1.6 into 10 to the power of minus 19. So I guess we have done everything correctly.
Sir, I
Oh,
have a doubt. Sir, lambda, you have taken 100 nanometer, right,
oh, yes. I have taken. Okay, it is separation between. Yes, that's what I was telling you. Thank you. Yes, wavelength is 1 nanometer. Yes, fine. It is 1 nanometer. I thought there is the wavelength. Oh, fine. Thank you. Thank you, Shaikh.
Yes.
Okay, so we have to just erase this thing, because I took it to be equal to 100 nanometers. So I took it 10 to the power of 4. So it would be simply uh, 2 point, let us write it explicitly again, into 1 nanometer is 10 to the power of minus 9. It is 10 to the power of minus 18. Okay, into this value, which is what I skipped, 92.1 lambda square. Mass is given into the electronic charge, 1.6 into 10 to the power of minus 19. So let's solve this. So it will be 6.626 into 6.626, which is, let me write it down explicitly, 43.903 something into 10 to the power of, it would be 68, 10 to the power of minus 68, and simply over the denominator, 9.11 into 1.6, it would be 29.152 into 10 to the power of, it would be minus 50, it would be minus 68, this thing as well. So this thing and this thing will go, and we will be left with 43.903, divided by 29.152, it would be 1.506. So this value is coming out to be equal to 1.506 approximately. So 1.506 volts approximately. So it means that option C might be the correct option. Option C. But for that we have to check this. What we can say, after passing through the slits, what is the minimum spread? So that's what Tanish was saying, that we have to check this minimum spread uh, by using this Heisenberg's uncertainty principle. Where now the separation between those two slits is 100 nanometer. Let's be specific about this value so that we do not lose it. This delta x, wait a second, this delta x is equal to 100 nanometer. Now if we use this Heisenberg's uncertainty principle, we know that as professor has told, for these objects which are having less effective mass, this you have seen in these lectures how these the light particles, or you can say these particles which are having very small effective mass, how their wavelengths matter to them. You have gone through this thing in the lecture itself, where the professor might have solved this ball example and the particle electron example, and you must have seen that how this impacts how this quantum or Heisenberg's uncertainty principle does not impact our day-to-day macroscopic life, but it affects our microscopic life. So for that, you must have gone through the lecture. Let us see that from directly taking the formula from the lecture, it is this Heisenberg's principle, delta p into delta x. There is some uncertainty in their measurement. For example, if I am measuring the position, I am saying this pen is over here, I cannot say what is its momentum with a particular certainty. There will be some uncertainty associated with this pen if I am talking it in quantum mechanics point of view. But since it is having some respectable mass, some so this pen might not have that much quantum effects. So whereas these particles, when we are dealing with these particles which are very light, then in those cases, as the professor has must have seen in the lecture notes, that how it impacts this microscopic things, not the macroscopic things that much, because it you can say over here it certainly will impact this case of R, since we are dealing with these electrons. There we cannot measure this position and the momentum accurately. We will be having some uncertainty associated with that material, or sorry, with that electrons. So we can say that this delta p, I can even denote it by only x. This is not the momentum in 3D, this is the momentum in x plane only. Since we are dealing with 1D problem, delta px has to be greater or equal to delta h bar by 2 delta x. So this delta x, we have taken it to be equal to this px is greater or equal to h bar. H bar is 6.626 into 10 to the power of minus 34 divided by 2 pi. Okay, 2 pi is 2 pi because h we know this is the value of h, 6.626 into 10 to the power 30 minus 34 joule second, and this 2 pi comes out from this h by 2 pi, which is equal to h bar, and this is equal to 2 into this separation as pointed out by the Mr. Shaikh. He correctly pointed out in the previous problem that I had taken the wavelength to be equal to 100 nanometer, whereas it was the separation between the slits that was 100 nanometer. Thank you for that. So this delta x is equal to 100 into 10 to the power minus 9, and simply if I solve this, it should come in the units of 6.626 divided by 2 divided by pi divided by 100 divided by 2. It comes out to be equal to 5.273 into 10 to the power of minus 28 with the units of kg meter second. Okay. So this is the value of the this is the value in the this is the what we can say uncertainty in the momentum which is associated with this electron. So this value over here, it does not match. I guess it does not match anything because it was 1.5, and now since this is the minimum spread over here, you can clearly check it is the minimum spread in the electron's momentum in the direction parallel to this, and since this is the minimum spread, and this minimum spread is 5.27, or you can say 5.3 approximately, so we would say that none of these options is correct. Now we have another problem which is associated with this
Sir,
momentum.
for the previous question,
Oh,
which
okay.
option is the correct answer, sir?
Which?
Which option do we choose?
I think I chose D because this minimum spread in the electron's momentum, minimum, because it's telling me to find the minimum. I got the minimum value to be equal to 5.273 or 5.3, let's say. So for me, I would select none of the above options because I feel that none of the above options is matching due to the condition that has been put, minimum spread. If it would have been just the spread, what is the spread? Is the spread greater than this value? Because it is certainly greater than this value. 10 is certainly greater than this value, but in the problem it has been told to find the minimum spread. So the minimum value, if I am seeing the condition greater or equal to, so it would be at the equal to value. So the this value, wait a second, okay, so this value would simply be equal to some 5.3 number, so I would go with option D. Okay, thank you. So okay, this is some wave function of a particle at state which is in state some state n, and it is given by this value which is root 3 cos of 2 pi x by a between the limits minus a by 2 to plus a by 2, and rest for minus infinity to minus a by 2 and a by 2 to infinity, it is 0. So I am required to find this average momentum. For this we will just do this observable thing, and previously when someone had asked, my colleague told me that I have told that this observable, the psi star acts on observable, which is clearly the wrong thing, that I shouldn't have told it like that. It is basically the observable acts on the psi. Okay, this observable acts on the wave function. Now this for this finding this average momentum, uh, I would simply say I will treat this momentum as an observable simply, and find this in one direction, which is x, since it has been given in to be in 1D only. So I would say this is simply equal to minus x to minus infinity to infinity psi star of x. Now this momentum function, this momentum observables rather, it would act on this wave function x dx. Okay, now we know from this wave function's definition, uh, this value, this is equal to root 3 cos of 2 pi x by a between the limits of a by 2 to minus a by 2, and it is 0 otherwise. Okay, it is 0 otherwise. Now from the definition of this, as we have seen in this lecture notes itself, how professor told us to obtain this momentum operator using this, you can easily see, if we have this plane wave thing, you can obtain this momentum operator easily by derivating that thing. And you must have seen this momentum operator is simply given by, if this is x, it would simply be given by minus iota h bar dou by dou x. Let's keep it over here. Okay, now since this momentum operator operates on this wave function, uh, now we need to solve for this thing, which is this expectation value or this average momentum, which is simply given by this minus a by 2 to a by 2. Since this function is 0 otherwise, this will be root 3 cos of 2 pi x by a, and this would simply be minus iota h bar d by dx root 3 cos of, okay, 2 pi x by a integrated over, wait a second, integrated over the x space. So it would simply be equal to minus a by 2 to plus a by 2, root 3 and root 3 will multiply, it would simply be 3 times minus iota h bar cos of 2 pi x by a d by dx of cos of 2 pi a would simply be minus 2 pi by a sine of 2 pi by a x dx. Let's check its correctness. Okay, it is correct. Okay, this will go with this thing, it will be simply 6 pi h bar by a, it would be equal to iota times 6 pi h bar by a minus a by 2 to plus a by 2 cos of 2 pi x by a sine of 2 pi x by a dx. Okay, let's use this fundamental formula for this cos of theta into sine of theta is given by sine of 2 theta by 2, or simply sine 2 theta is given by is equal to 2 times sine theta into cos theta. So from that formula, we can simply say this is iota times h bar. 2 and 6 will give us this 3 thing only. 3 times pi divided by a minus a by 2 plus a by 2. This is sine of 4 pi x by a integrated over dx. Okay. Now let us use some interesting property of this sine function. We know that this sine function, this is an odd function, and in here we are having the limits between minus a by 2 to plus a by 2, and uh, we will be having this whole function to be equal to this whole function, not this thing, sorry, this whole function to be equal to 0, because we can simply say that this sine is an odd function. Wait a second. Wait a second. I have to take some call. One second. हेलो हेलो हाँ 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 आप दे दीजिए वेस्टर्न लैब में, मेरा दोस्त उधर है, वो ओटीपी दे देगा आपको. हाँ हेलो, वो आप वेस्टर्न लैब चले जाइए, वहाँ ओटीपी दे देगा वो, आप चले जाइए. हेलो 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 हाँ 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 आप चले जाइए, ओटीपी दे देगा, वहां पे एक बंदा है. ओके. Sorry for this interruption. I had to take this call. So this sine is an odd function. So between the limits of minus a by 2 to plus a by 2, it would give us 0. So this value would come out to be equal to 0. So yes, option A is what we are going to select. And now let's move towards another problem where this is now this is complete transition. Till now we have been doing this quantum mechanics thing. We have been seeing that how we can what we can say, what how we can obtain these wave functions for some systems which are known to us, like as we have previously seen in this case of this 1D potential well, and you can do the similar things for this harmonic oscillators, like those things. And this quantum mechanics, it was there just to provide you insights how this band structure will evolve when we will move forward in the course. uh, we will we would see that how this quantum mechanics, this wave function, since it has all the properties that is associated with a particular particle, since wave function contains all the information, so we would as we move forward, we would say how these wave functions would help us to calculate these electronic band structure properties, and how all the information will be there in these wave functions. Now, before moving towards this, what we can say, another part of this course, which is related to these crystal structures, because we know that these materials mostly we will deal with this silicon. Currently, since there are current research scopes presently, we mostly go beyond the silicon at from the research point of view, and we see the silicon is the backbone of the our semiconductor industry, and that silicon, it crystallizes into FCC kind of a structure, which is also known as diamond cubic. Uh, for that, let us try to evaluate this problem. Just see what insights can we get from this silicon material itself. So this silicon, as this might you might have gone through the lectures for this second week as well. You must have seen how the professor has gone into these different kinds of unit cells, like this cubic unit cell, this face-centered cubic unit cell, and face-centered cubic unit cell, and this body center. And you must have seen that these are having certain number of atoms which are present in a particular unit cell. So this unit cell is basically the repetition of that thing. So there is a difference between the primitive unit cell and the unit cell. Primitive unit cell is the basic building block. So if I repeat this primitive unit cell only, I will be able to produce the whole crystal structure. So like in case of silicon, if I take its primitive unit cell, or in case of for example, we have a the research to the 2D materials, for example, where we just have these we can say, which evolved due to this discovery of the graphene by this Scotch tape technique, where they had just, for what we can say, I am having this pencil, and I am having another pencil, and there is another pencil, there is another pencil. We can say like I am having 20 pencils, like they are stacked in this direction, we can say. And they just took off one of the pencil from this stacking. They just peeled it off. For example, like we peel the onions at our home, they peeled off one layer, we can say, or one pencil they peeled off, and they got some novel material, which was which had some confinement in one direction. And it was, you can say, it had unique characteristics. It showed that it showed up to particular, what we can say, particular extent, or particular seeming, we can say, particular value of time. It showed that it is some promising kind of a material in electronics. I am talking about graphene thing. But this graphene, once this was evaluated for this logic applications, due to the absence of the band gap, because we mostly want the materials for our semiconductor purposes, we want them to be having some band gap, so that we will be able to use them as switches. So that is the main thing. We want that there should be some difference between this, since if we see this valence band and the conduction band, pictorially we see that there is only one valence band, there is only one conduction band, but in the reality there are many valence bands and there are many conduction bands. And the highest valence band and the lowest conduction band, the difference between those two in case of graphene is zero. So the band gap in case of graphene is zero, and so this hampers its application in uh, logic device applications. But there have been methods that have enabled the people to use graphene in logic device applications, like people strain the material. Because these are 2D materials, they have shown a bit of a promise in case of strain sustainability. So if I am expanding some material, like we expand the rubber sometimes, it deforms and gets back to its shape, like. So this kind of physics is being applied to the materials these not these days, from many years, but they are being explored. These 2D materials have shown promise in case of this flexibility. You see that you are seeing these organic materials, they are also quite flexible. They displace these kind of materials. These days we see that we are having these flexible foams, like they wrap around our arms. So these materials, these novel materials, apart from silicon, are playing dominant role in our day-to-day lives. But the silicon still remains the predominant backbone of our semiconductor industry, due to one of the major thing that it has, that is it has this unique characteristics to form this dative oxide. This is SiO2, and also this silicon has the most is you can say you pick up you can say sand from your garden, you will say that it has silicon present in it. So the availability is also one of the major thing that boosts our semiconductor economy. And this silicon which you are seeing over here, this unit cell over here, you can see this unit cell over here for the silicon. This is just the backbone of our semiconductor industry. Whole physics that you see currently, whether they are although the photonic devices use other materials as well, as professor have told you in these lectures, he might have showed you this gallium arsenide as well, how there is some little difference between these two valleys. And you must have seen that there are other upper bands in the material as well that contribute to the its electrical and we can see optical characteristics. So just looking at the band structures of the materials which are obtained from the wave functions itself, the wave functions play a crucial role. So for that we delve into the quantum mechanics. Now this other part of our lecture, it is also the backbone. This unit cell, or you can say this you can say this how these atoms are arranged in a material, these also play really very crucial role in case of any material. There are different materials. For example, if I take graphene of or for example if I take graphene and I just replace some of its surface bonds by uh, let's say OH, so it would show completely different properties. So this surface functionalization, or you can say changing the properties of a material, of these materials, they all depend on these how these periodic arrangement of the materials, this periodic arrangement of materials plays a really crucial role for any material to be studied. So in here you are seeing this unit cell, this silicon unit cell. Can anyone among you tell me how many atoms are present in this one unit cell? For the silicon case, let's not just see this picture. You just tell me how many atoms are present in one unit cell for this for the conventional things that you are seeing in the lectures that professor told you. Anyone?
8 एटम्स कॉर्नर पे होते हैं और 6 बीच मतलब उस पे होते हैं फेसेस पे
और
और
सही सही, you are absolutely correct, Tanish. So अगर हम
For
अगर
FCC, for an FCC type, we will have 4 atoms per unit.
हाँ ओके, बट व्हाट इज सिलिकन? सिलिकन बेसिकली अगर हम देखेंगे, जो सिलिकन हमारे पास होता है, दिस इज you should remember this is a kind of a thing that one always sees in these semiconductor devices courses, that if I have one silicon which is FCC unit cell and I have another FCC unit cell, basically silicon consists of two interpenetrating FCC unit cells, with one FCC unit cell displaced from the other unit cell by quarter distance in x direction, in y direction, and in z direction. So basically what you are seeing is you are seeing this in two interpenetrating FCC unit cells in case of a silicon. So these two interpenetrating unit cells basically will have total number of 8 atoms in it. So basically it will have 4 atoms within the unit cell, and as both of you rightly point out, for the FCC we will be having 8 atoms at the corners, and those 8 atoms but would be shared between the rest of the 8 things, because if you can say a corner, it is a 3D thing and it would be shared with the rest of the 8 unit cells. So for a particular unit cell, the contribution of one those corner atoms would just be 1. And similar for the face centered thing, when they just lie on the faces, and we have 6 faces, but the faces are shared between 2 unit cells. So as a result of this thing, we will be just having the 6 atoms being shared between the faces itself, and as a result we will be having just the contribution of 3 from those faces. And now, since we have the another interpenetrating FCC lattice, we will be having total 8 atoms in this kind of a silicon unit cell. So I guess I should write this contribution over here. So it would be this 8 atoms at corners, 8 atoms at corners, and shared one thing, shared with rest 8. Okay, and I will be having this 6 faces and 6 faces atoms, and those will be shared with the shared between 2 unit cells, 6 atoms. Wait a second. 6 atoms shared between 2 neighboring 2 cells, unit cells, and 4 atoms within the unit cell. So the total contribution will simply be equal to 8 into 1 by 8 plus 6 into 1 by 2 plus 4. It would simply give me 8. So the number of atoms would be in this unit cell, silicon unit cell, would be simply equal to 8. Now we have been given some values, like we have been told that this silicon has a lattice constant. This lattice constant is just the spacing between the 2 atoms, and this silicon is having this lattice constant to be equal to, sorry, this lattice constant is you can see this unit cell's dimension. I am not talking about this atomic distance. I am talking about this cubic box, for example. This is having this lattice constant to be equal to 5.43 angstroms. Okay, this is the spacing of for this silicon cubic unit cell. Since this is cubic, we will be able to find its volume easily. And now we have been told to calculate this. We can say, let me name this as well. This is diamond lattice. Okay, this is diamond lattice. You can see, whenever you see these kind of things, this zinc blend, they also crystallize in this diamond lattice thing. But in that zinc blend, we have Zn and we have sulfur. We have zinc and sulfur. They are their bases are of different kinds. In silicon, the bases are of same kind, this silicon atoms itself, whereas in zinc blend kind of a structure, it is of different kind of atoms. So this kind of a lattice is known as diamond lattice. Okay, so this diamond lattice, we have been told to find this density. The density is simply the, you can say, this number of atoms with their respective mass divided by the volume. So this is the atomic density, density of silicon that we are going to find in this material. So this Let's constant, since this Let's constant, wait a second, Let's constant is equal to 5.43 angstroms. Okay, and this atomic mass atomic mass is equal to, wait a second, 28 point, wait a second, okay. Uh, so this effective mass is equal to 28.0825, 28.085 in atomic mass units. Now, if I do the conversion to the grams, it would simply be 28.085 into 1.66 into 10 to the power of minus 24 grams. So it would simply be equal to 28.085 into 1.66. It would simply be equal to 4.66 4.66 into 10 to the power of minus 23 gram. Okay, this is its atomic mass in grams. Now the density of silicon is simply given by number of atoms into mass divided by the volume of unit cell. So it would simply be equal to 8 into 4.66 into 10 to the power of minus 23. Volume will be simply a cube, since this is cubic in nature. We have seen that these are two interpenetrating FCC lattices with the side being equal to A equal to 5.43 angstroms. So it would simply be equal to A cube. A cube is 5.43 into the 10 to the power of minus 10. You can say, let's talk in centimeters. It would be 10 to the power of minus 8 centimeter cube, so that this has the units of gram per centimeter cube, and this would give us the value to be equal to 10 to the power of minus 24, 16, 24, and it should give me the value to be equal to 5.43 into 5.43 into 5.43, it is 8 into 4.66 into 10 to the power of minus 1 divided by 1.601. So it is simply equal to 8 into 4.66 divided by 1.601, which is 23 or 2.32 gram per centimeter cube. So this is the density of silicon that we have been able to find for these by just equating it by just we just saw that there are eight atoms and its effective mass was given, and also the volume was given to us. So we found out to be equal to 2.32. Now this is another part as well, where we have been told to find the atomic density. This is different thing. This is not the density. This is atomic density, which means number of atoms per unit volume or per unit area. Over here, since we have to deal in planes, you must have seen that. For example, if I have this FCC lattice, for example, over here. Let me draw this for the first thing. Let me draw for this 100 plane. For example, uh, wait a second. Wait a second. So if I draw this cube like this, for example, with this being the x as pointed out earlier, and this cube, for example, uh, is looking like this. My drawing might not be perfect, sorry for that. So wait a second, let us rub this and draw it at the end. So it would be like this, like this, like this, and like this. Okay, so if I am talking about 100 plane, let's say 100 plane, it would mean I am talking about this plane. You must have seen planes in the lectures, and this is some plane which is which lies in the x direction, which I am taking to be equal to as 100 plane. This plane faces me currently, and this plane is having some particular number of atoms on it. Since whenever we can say whenever we take some silicon material, we cut it in some planes, like 100 plane, like I have shown in this kind of a case. For this can be cut in 010 plane, like we can cut it in 001 plane, but those planes would be, if we consider just the cubic thing, for a cubic material it would be equivalent things. Right over here we have been told to calculate in three kind of planes that are mostly, or we can say, they are mostly seen or studied in these silicon materials. So these silicon material, they are generally found in or studied or experimentally realized in these three orientations, which is 100 and 110 and 111 orientation. Now this 100 plane, it would be having, you can say, since this is A, this is A, this is A, this will also be A, and similarly this will also be A. Okay, so this face which I have highlighted over here will be having some atoms like this on this plane. Okay, so these atoms, they will be shared. This will be quarter, this will be quarter, this will be quarter, and this will be quarter, making it 1. Okay, and this atom lying on this face is itself equal to 1. So the number of atoms on this plane, number of atoms on this plane is equal to 2, simply. Now the area of this plane, is simply equal to A into A is equal to A squared is equal to 5.43 into 10 to the power minus 8 whole squared. In centimeters, it would simply be 5.43, 29.48 into 10 to the power of minus 16 centimeter square. Okay, so this is the area of this plane which we are talking currently is 100 plane. So now this atomic density along this plane, this atomic density also plays crucial role when we are dealing with this material in terms of this scattering mechanisms as well, because more number of sites would mean more number of scattering sites that are present for the particles or these material to have the scatter centers. As a result, there will be more degradation. So there has to be some interbalance between these things. So this atomic plane configuration, what we are seeing over here, whether we are placing it in, well, like say 100 plane or 110 plane or 111 plane, it will matter for the transport characteristics, because they due to the atomic arrangement in that particular direction, the properties of the material can be quite different as compared to another direction. So this atomic density would simply be given by 2 number of atoms divided by the area, which is 29.48 into 10 to the power of minus 16. So it comes out to be equal to 2 divided by 29.48. It would be 6.78. 6.78 into 10 to the power of 14 per centimeter square. Now, for this 100 plane, I have already kept a slide of that, so that I don't have to draw it again and again, and we don't face any issues due to my drawing. And this 100 plane, you can see this 100 plane over here looks like this thing. This, it intersects the x-axis, it intersects the y-axis, however it does not intersect the z-axis. This is what this 0 means, that it is not intersecting the z-axis, it is just intersecting the x and y-axis. Similarly, in the previous case, when we studied this plane, this 100 plane, we saw that it just intersected this axis, this x-axis. It didn't intersect this y and this z axis. So it meant that this plane, whenever we see a 1 written, it would mean that it is intersecting that axis. So this 100 simply means that we are intersecting this x and y axis respectively. Now, for this 100 axis, you can see this, we have to get this value for this phase diagonal sort of a thing. We need to get the value of this phase diagonal, and from the simple algebra trigonometry, from the simple trigonometry, we will see that since this is a and this is also a, this would simply be equal to root 2a, making this side to be equal to root 2a, and this side would be a itself. As a result of this thing, we will be having the area to be equal to, the area for this would simply be equal to root 2a into a. It would be simply root 2a square, or you can see root 2 times the previous value that we had obtained, 6.78, 6.78, no, 29.48, 29.48 into 10 to the power 16, 29.48 into 2, or 29 point into root 2, sorry, into root 2, it is 41.69. It is that value a square, that we have 5.43 into 10 to the power of minus 8 square in centimeters. So it would be 41.69 into 10 to the power of minus 16 centimeter square. Now, if we see that this number of atoms in this thing, it would be 4 at the corners, this atom, this atom, this atom, this atom, okay, as you can clearly see over here. And it would be these 4 atoms would be shared with other 4. As a result, its contribution will be just 1. Now these two faces, this bottom and upper face, they would be having some atoms also. This there are, it is you can check by yourself. It is currently 2 in number. So these two numbers, these two atoms which are lying on the faces, would be shared between 2 rest of the unit cells. So as a result, its contribution will be just 1. And you can see there are 2 atoms due to this motif, this interpenetrating FCC kind of a thing. So as a result of this, number of atoms in this plane is 4, and the area as compared to the previous thing, the previous plane, is also root 2 times more. So we expect some different atomic density in this kind of a plane. So if I solve for this atomic density, sorry, okay, so if I solve for this atomic density in this plane, it would be simply atomic density equal to number of atoms, which is 4, divided by the area, which is 41.69, 41.69 into 10 to the power of minus 16, and it would simply be equal to, it would be equal to 9.59 into 10 to the power of 14 per centimeter square. Clearly, you would see that this has more atomic density as compared to the previous plane. So a silicon material itself in different planes will have different kind of a characteristics, which you would see in the upcoming lectures as well. Now we would look into another plane, which is this 111 plane at last, which is 111 plane, where this x-axis is being intersected, y-axis is being intersected, and z-axis all are being intersected, and this plane is kind of a triangle thing. Okay, this is kind of a triangle thing. Now this plane has number of atoms, which is given over here. This plane has just two number of atoms. Okay, you can see this corner, this corner, and this corner. They are we are having this atoms, which are given by this number, and we are having this and this, which is being shared between two, and as a result of this we are having these three atoms which are shared between two, and these three which are being shared between six atoms, as a result of which we are having two, just the two atoms in this kind of a configuration. And when we check this dimensions of this thing, this would be root 2a, as we have previously seen. And when since this is root 2a, and if I draw its perpendicular to this in order to find this value, we will find this is equal to root 2a by 2, and as a result of this we get this hypotenuse to be equal to root 3 by root 2. So this area of this plane, wait a second. So the area of this plane is simply area of this plane is simply given by this value, which is root 3 by 2a square, and we get it to be 25.53 into 10 to the power minus 16 centimeter square. Now this atomic density, since we have another session, I am hurrying a bit. This atomic density, I had one question as well that I had to answer in the chat. Let's do it in the next class for that, because next session is at 5. So the atomic density would simply be 2 divided by 25.53 into 10 to the power minus 16, and it would 10 to the power of minus 16 centimeter per centimeter square. It would simply be, wait a second, 2 divided by 25.53, it would be 78 or 7.834 into 10 to the power 14 centimeter per centimeter square. So these are different kind of atomic densities that we are getting in these kind of different planes along different silicon planes. So if you have any question regarding this, you can ask me, because there is, I guess, another session from 5 that you need to join. Mr. Tanish or Mr. Srihari or Manikandan or
Sir,
okay.
if at last moment we come up with some doubts on the assignment, So can we reach to you through
Yes,
mail
yes,
or
yes, yes.
something?
You can email me. There is no issue in that. I have given my email in the slides. You can email me. I will be happy to answer.
Okay, sir.
Okay.
Hmm.
So,
I
mhm.
I don't see email.
It
Maybe I
is.
don't.
Wait a second. Whenever you download my slides from that NPTEL site, you will be having this email atbb20 at iitk.ac.in. You can email me on this, and I will be happy to answer any question. Any question.
Okay, thank you.
Okay. If you have no question, you can leave this session as there is another session scheduled for today. uh, at 5 you can attend that session. That will be also very uh, valuable session for you. So I request you to leave this meeting if you have no question. Some other person will join. Please join the other session. This session has been concluded, so I will remove the participants so that you can join the other session from my colleague. Thank you.